Okay, let me go into diagram and forces. We use these things called free body diagrams as a way to distill what are the forces acting on objects that we're interested in. So be careful about how we phrase this. So we're going to worry about the forces acting on an object, right? There are other forces going on. Remember, everything has a pair force. So we're going to ignore those that we don't care about. So this is an example. So if I have this this guy that's looking at this box, I can draw a free body diagram for the box itself, and it's going to look something like this. So notice I've got a force going up and a force going down. I'm going to go through these in just a minute to describe what they are. So I can also, if I get and push on the box, then you can see other forces that are involved. And if I get to show those, come on, dude, push. So, but let me talk you through some of these. So a free body diagram is a way of simplifying something and making a force diagram. A couple of important things we're going to do with those. So first, let's find where my thing is. Okay, so so if we have a box that's sliding across, let's do this one, right? So I have a box that's sliding across. We're just sitting there. It doesn't matter. Let's like push it. So I'm pushing it along. And what I want to do is I want to distill the box down into something simple. So I'm going to forget about everything else there. Either draw a dot, which is a common way to do it, or if I wanted to, I would just compress whatever it was into a square to sort of represent the forces that are acting on it. And I'm going to think about 4 different forces every time that I think about these things. So I'm going to think about the force that comes from contacting something. And these are the usually the easier ones to figure out. So we're going to worry about the normal force. We're going to worry about the force that we apply. And I'm going to worry about a force of friction if it's present. And then we're going to worry about field forces as well. So for most of this class, we're just going to worry about gravity. So I'm going to have a force that comes from gravity. Right? These are forces that act at a distance. It's kind of a magical thing that you can have, a planet, and then you pick someplace else, and then that will be affected by the gravitational field of that planet. Weird. So we have gravitational fields passing through us. We have electrical fields passing through us. We have magnetic fields passing through us. And most of those you can't, all of those you can't detect unless you put a specific thing there to see if it's there. So anyway, fields are kind of magical. So these are the 4 things I'm going to look for, though. So I want to see, gravity, normal force, applied force, and frictional force, and just figure out what's going on. So on this one, right, if this is moving at constant velocity, so I'm pushing it in one direction and it's dragging along the floor, so there's going to be some friction acting on this. I'm going to end up having all 4 of these forces, right? So I'm going to have force of gravity pulling it down. I'm going to have some force that's pushing it up, and we'll get into that in just a minute. We'll call it a normal force. I'm going to have the force that I applied to move it in this direction. And then I'm going to have the frictional force, which is always going to be opposing motion. So frictional force always opposes motion. And we'll get into a brief calculation for that. So this is a free body diagram of a box that's being pushed at constant velocity. Notice that my arrows are always going away from my object. If I do it on a box, my arrows are going to go away from each other. So if I push on this, I'm going to pretend that's the same as pulling. Right? So my arrows are always going away from the object. Second thing that I want to do is I want to make sure I indicate those ones that are equal, right? So if my object's not accelerating in some dimension, then the forces must be balanced. So it's not accelerating up or down, so I'm going to indicate that these are equal forces by putting a hash mark in these. Also, it's going at constant velocity across the floor, which means it's not accelerating, so these 2 forces must balance as well, and I'll put double hash marks in those to indicate that. So this is the free body diagram of a box that's being slid across the floor at constant velocity. Let me talk for just a minute about the normal force. So you're going to think about this. So suppose I have 2 solid walls, and I suspend a string in here, and then I have a guy that stands here, right? So he's standing in the middle of the string, right? So he's having gravity that's pulling him down, and conceptually you get the idea, right? That the string is bending, and the string is providing that force that's pushing him upwards, right? So there are 2 forces. He's not accelerating. The 2 forces pushing him backwards or up. And this is what we mean by the normal force. Is the normal force is that force that's coming from that substance, in this case the string, to like keep him at that position. So I mean, if we replace the string with a board, right? that force that's holding him in place is coming from that board, right? So he's touching the board here, and his gravity is pulling him down, and the board's pushing him up. Right? And it's weird to think about, but even those things that don't look like they're flexing, right? So if our dude is standing on a concrete floor, right, that concrete floor is flexing just a little bit, and it's being compressed, and it's pushing him back up with the same magnitude that he's pushing down on it. Right? So this is what we call the normal force. And one important thing about the normal force is that it's always perpendicular to the surface, right? So if my dude is now standing on a ramp, right, my normal force is going perpendicular to that surface. So normal force is going to be going off the ramp. Whereas gravity, well, gravity is headed straight towards the center of the Earth, right? In that direction. So now they're at an angle to each other, and I've got to figure something out. So anyway, the normal force is the force that is from something being compressed and holding something in place. So if I take a box and I push it against a wall, right, that wall is pushing back, right? So I'm applying a force, I'm flexing that wall just a little bit here, the wall's getting flexed a little bit, and that wall is pushing back in the opposite direction the same amount so that it stays stationary, right? It's not accelerating, so my forces must be balanced. So let me draw a very specific diagram to talk you through some of this. So here I go. So I have a boulder on a hill. Let's say it's stationary, just for fun, right? So let me think about this boulder. What's happening to this boulder? Well, I'm going to think about my four forces. So I have a contact that's happening here. So I'm going to think about the contact force, right? So at this contact point, right, my rock is pushing down, and my normal force is going to be pushing up away from it. I have a big boulder, right? And gravity is acting at a distance, so we'll be careful, right? Gravity is not acting at the contact point. Gravity is acting all over here, and to simplify things, I'm going to pretend, well, here's the center. I'm going to say gravity is acting from this point, pulling it down, right? So notice these are just force arrows, so the fact that I crossed them doesn't matter. Right? But gravity is going to be acting at the center, pulling it down. What else do we have, right? So it should... right? If this was frictionless, right, it should want to go that way. So there must be something that's holding it in place or keeping it from sliding down. And it wants to go in this direction, so the friction must be going in the opposite direction. So I'm going to have friction going in the opposite direction. In this case, I don't have an applied force. I don't have somebody sitting on the outside pushing on it anywhere. Right? So notice that it's not going anywhere, so all these forces need to balance. And we'll get into these sort of ramp problems, but trust me when I say that we can get all these forces to balance when we separate the x and y axes and sort it all out. But right now, if I was to draw a force diagram, I'd say, well, let's compress it down to a single, or free body diagram. I'm going to compress it down to a single dot. Right? I'm going to have my normal force going this way. I'm going to have my frictional force going up the hill, and I'm going to have gravity coming straight down. So again, I've compressed this down. So in reality, these are happening. These forces are being applied at different places, right? So my force of gravity effectively is at the center of mass. My friction force and my normal force come from that point of contact. And when I compress it down into a single view, I get something that looks like this. So this is a free body diagram for a rock that's sitting on a ramp. Anyway, the key things I'm going to look about. So I'm going to think about contact forces. So what's contacting it, and then frictional forces. So I'll have applied force. I'll have normal force from contact, and I can have frictional force if there's friction that's involved. And then we'll worry about field forces. And for now, we'll worry about gravitational, but later on we'll get into electrical forces that can happen at a distance as well. And that should help you hopefully draw a couple of diagrams. Talk to you soon. Bye.